Howdy, physics students. We, in our part of the world, are talking about work and energy, and in particular, standard 4C. What? That's part of the College Board's curriculum. Let me refer you. See that 4C up there? If you're an AP physics student, standard 4C. Hello. Look at this. It's an enduring understanding. Right? Interactions with other systems or other objects or systems can change the total energy of a system. Interactions means with other objects. Interactions with other objects. That means when something applies a force to something else, well, then the energy of a system can change. That's what we're talking about. Okay, we have talked about that when one object exerts a force on another, what can happen is, well, an object's kinetic energy can change. All right, we've said that in particular, we have equated work by an external force, in some cases, to a change in a system's kinetic energy. We have equated, in some sorts of cases, work done by an external force to sometimes change an Earth mass system's gravitational potential energy. And we're going to talk about a third case here. And that case is, what if there's an object attached to a spring? Okay, and let's call this the spring's equilibrium length, its natural length. Okay, and then let's say also that this object is moved. Let's say this object is moved from here to here, and then that makes this spring expand. Delete thing marker. So now we have we have moved this object. Now what has, well, I don't know, some force has been applied to this object in this direction. Now this is what we call an external force. That's Jim pulling on this block, and that has displaced this object through some distance delta x. Okay. Now what we can do here is we can say, what does this plot of the external force that Jim applies look like as a function of position of the spring as measured from, well, we're going to call that the origin, the place from which this thing starts. And, well, in the very beginning, when the object is here, well, the spring applies no force because it's at its equilibrium length, and so Jim really has to apply an infinitely small amount of force to start moving this object a tiny little bit. All right, so then the object moves a tiny little bit, but as soon as the object moves, well, the spring starts applying some force to the object via, well, we know this, that F spring is negative kx vector, which means that as this object is moved to the right, we get a spring force to the left, a restoring force it's called, a linear restoring force, linear meaning a direct relationship between magnitude of force and magnitude of displacement. A restoring force means trying to get the spring, back to equilibrium length. All right, so so with Jim's little tiny force that extends the spring a tiny little bit, which makes the spring exert a tiny little force, and if those forces stay the same size, the object only moves to that location, but Jim pushes a little bit harder, right? Oh boy. And then that pushes the spring or the object a little farther out, but that makes the spring push harder, and so, but Jim wants to keep moving it, so he pushes even harder. That's getting to be one ugly vector, and so this moves the object a little more, but extends the spring a little more, and this restoring force gets bigger. You get the idea, maybe. So if we look at the force that Jim applies as a function of position, it looks like this. It looks exactly like what the spring force looks like. The force that the spring exerts on the object looks like. Okay, so let's say that this is our delta x, right? There's some amount of force that Jim has to apply. Well, there's a specific amount of force that Jim has. Who's Jim anyways? Jim's the guy doing the pushing, right? So there's some amount of maximum force that Jim, Fs max, I'll call it, has to apply to get the spring to displace by that distance delta x. All right, but the deal is Jim applied not a single force, but based on how long the spring was, he applied a bunch of different forces. And this plot shows us how those forces vary as a function of the location of the mass, really as a function of how much the spring has been stretched. Okay, so what this shows us is that Jim has applied a force that has moved an object. All right, and what that is the very definition of is the fact that Jim has done work. Well, all right, I want to call it Jim, but I'll call it external. There's work done by an external force that's not part of our, what does external mean? Well, we're talking about the system here equals the mass and spring. Right? So if there's something that's not mass or spring that's applying a force, that's called an external force. And Jim ain't mass or spring, so any force that Jim applies to this system is an external force. All right, so this this application of the force that results in motion, or results in displacement, I should say, is the definition of Jim doing work. All right, so Jim has applied some force through some displacement, and therefore he's done work. Except there's not a force, a single force that Jim has applied. Jim has applied, as we showed in our graph here, a range of forces. And so there's a couple things we can do. One is if we want to figure out how much work Jim has done, we could do this and say, well, what's the average force that Jim has applied? And that average force looks like this. Here's F average. Anytime there's a uniform change in a function, like our red linear function there changes uniformly, the average value of that function is, well, the average of the lowest and the highest value, right? So, okay, we could do one, well, that in our case here would be, let me change colors. That would be 1/2 Fs max, that's our average force, times delta x. Yeah? Well, what is Fs max? How much force does it take to extend this spring by a distance delta x? Well, guess what? It takes an amount of force, kx. How much force does a spring apply? Well, that depends. It depends on how far the spring has been displaced and how stiff the spring is. And again, what we're saying here is when Jim gets the spring to this location, there are actually two forces acting on the spring. One is Jim's force, F ext. The other is the spring force, Fs. And if we stop the spring at that location, it means these two forces are of equal magnitude. So even though we're talking about the external force that Jim applies, it's the same as the spring force. And we know how to express the magnitude of a spring force. It, again, depends on these two criteria. Okay, so we can write this as 1/2, well, k, and our x here is delta x. And, well, then that's the k delta x is this. And then we have this delta x, so we have another delta x. And that's 1/2 k delta x squared. Now my people recognize that. What is that? Well, we have this idea or quantity we've developed. The potential energy stored in a spring is 1/2 kx squared. So this is a change in the spring's potential energy. Look at this. The work done by the external force accomplished something. What it accomplished is the work done accomplished a change, EXT, a change in this spring's potential energy. Maybe more appropriate to say a change in the mass spring system's potential energy. Yeah, I like that better. Okay? So what we're getting at is, what is it that work does? Well, work by definition, in order to say work was done, there must be a force that's applied that results in the displacement of an object. Okay, so those are criteria, but what does it mean to do work? Well, it means that you change some sort of energy. Okay? I want you to notice also something about what we're doing when we calculate this 1/2 k delta x squared thing. Well, we came at it from this idea of average force times displacement, but we can also come at it like this. Let me get rid of my average force thing here. Delete. What we can do is say, well, this is a graph of F times X, or sorry, F versus X. Work is F times X, so we're multiplying two things together, F and delta X. What we're actually graphically, analytically doing is taking an area under that curve. It's not a curve, it's straight. Straight lines are still curves, they're just not curvy. All right, so that area is F times delta X. And notice, if we did this area, if we said that the work is the area, well, work is 1/2 apparently base times height. Work is 1/2 delta x. The height of this thing is Fs max. Work is 1/2 delta x times k delta x, and we get right back to that. So the great thing about graphs is that they can be analyzed typically in a couple of ways, especially if we're doing this. I mean, there's really only one way to find a slope. But notice, we're not doing anything about slope here. What we are doing is saying, I want a product. I want something that's about a product. I can either, use this definition of, average force times displacement and get the expression that I want, or we can say that's the same thing really as calculating an area. Okay, what we are really trying to nail home here is, what can work accomplish? Work always accomplishes a change in a system's energy. Okay, it depends on what's involved in your system. If there's no springs involved anywhere, well, guess what? There will be no delta US. If if an object never changes height, there's never going to be any of that. If a system doesn't change speed from beginning to end, there won't be any of that. All right? But notice that these are all K. I don't know why I wrote KE. What is this? What is this? These are all the K, the UG, the US. They are all forms of mechanical energy. So we can really summarize all of this stuff in one of our simplest ways, most condensed ways. Work always changes mechanical energy. And not only does it change mechanical energy, it's equivalent to that change. Okay? Okay. Fairly well. Standard 4C. Sleep on it.